How Newton might interpret gravity was sufficient to permit us to fly from the Earth to the Moon at any point. Get yourself lost in the ticking hands of time, contemplating whether how we might interpret it is simply the tip of the transient iceberg on its head. His discovery isn't simply a hypothesis. A key could open the ways to the secrets of the universe, uncovering a universe more unpredictable and inspiring than we ever thought about envisioning. How does Brian Cox's new hypothesis challenge our conventional understanding of time, and what are the potential suggestions for our perception of reality? Join us on a fascinating investigation through the archives of time itself as we delve into Brian Cox's recently uncovered remarkable hypothesis on the nature of time in the vast universe around us. Secrets are waiting to be revealed, and some of these secrets involve confusing things about time and gravity, which are fundamental parts of our reality. Imagine a world where time acts oddly, can either slow down or accelerate. Additionally, the force that keeps us on the ground may not be what it appears to be. This is the realm of Albert Einstein's theories of relativity, where how we interpret time and gravity veers off in unexpected directions. Albert Einstein, a notable name, gave us a better way of looking at the universe through his theories of relativity. His work laid the groundwork for understanding how time behaves under various circumstances, particularly when traveling at incredible high speeds. It all started in the early 20th century when Einstein proposed two groundbreaking theories: the special theory of relativity and the general theory of relativity. The special theory of relativity, published in 1905, changed how we interpret existence. In simple terms, it tells us that the laws of physics remain the same for all observers who aren't accelerating, regardless of their motion. This theory introduces the possibility of relativistic effects, including the well-known idea that time can expand or slow down under certain circumstances. One captivating thought experiment used to explain time dilation is the light clock. Imagine being inside a spaceship moving incredibly fast, nearly at the speed of light. Inside the spaceship, there's a beam of light bouncing between two mirrors perpendicular to the direction of motion. According to the laws of physics, the speed of light is constant for all observers, so the light beam must appear to travel a diagonal path. Now, here's the interesting part. The time it takes for the light beam to travel its path should be the same for both the observer inside the spaceship and the one outside. However, since the path is longer for the outside observer, it appears as if it would take more time for the light to complete its journey. This apparent time difference between the two observers is what Einstein called time dilation. Time slows down for the observer moving relative to the stationary observer. So, in this situation, time behaves differently depending on your motion. Understanding how things change when they move fast, known as relativistic effects, isn't just a theoretical idea. Scientists use massive machines called particle accelerators, like the Large Hadron Collider, to make particles travel super fast, nearly as fast as light. When things move this fast, we need to think about time in a different way to make accurate predictions and measurements. Albert Einstein developed the special theory of relativity in 1905, and it changed how we see the universe, particularly when it comes to time and motion. This theory challenges what we might normally think. It says that the laws of physics are the same for everyone, whether they're moving or not. This is different from our everyday experience, where we might think that if something is already moving and we add more speed, it just gets faster. But Einstein's theory says there's a maximum speed that nothing can exceed. This is the speed of light. From this perspective, events that seem to happen at the same time for us may not appear that way for people moving close to the speed of light. Another consequence of this new way of seeing things is length contraction. This means that if something is moving, it looks shorter in the direction it's moving when you observe it from a place that isn't moving. And then there's the famous equation backslash E equals mc squared backslash, which comes right out of the special way of thinking. It shows that energy and mass can be converted into one another, which is a big deal for understanding how tiny particles behave when they're zooming around at superfast speeds, and also for things like what happens when particles split in nuclear reactions. In reality, special relativity isn't just an abstract theory. It's something we use in everyday technology like GPS. When GPS satellites send signals to your device, they're moving, so time acts a little differently for them. If we didn't account for this time dilation effect in our GPS calculations, your navigation would be inaccurate. So, special relativity teaches us that time isn't the same for everything and everywhere. It depends on how things are moving. This idea challenges what we normally think about reality. It's like saying our normal understanding of the universe is a bit off. According to the special theory of relativity, time isn't fixed. It's influenced by motion. Some key ideas, like the speed of light always staying the same and how energy and mass are related, have been proven by countless experiments. But there's more. Enter Albert Einstein's general theory of relativity from 1915. This theory delves deeper into the connection between gravity and the structure of the universe. It overturns the old idea that gravity is just a force that pulls things from a distance. Instead, it tells us that gravity happens because space-time itself is curved or bent. It's like saying, hey, gravity isn't some mysterious force. It's just how things naturally move in the universe. According to Brian Cox, understanding general relativity means thinking about the universe as a four-dimensional thing, combining 3 dimensions of space with one of time. In this framework, massive things like stars, planets, and even us influence how space-time is shaped around us. Imagine space-time like a big stretchy blanket. When something heavy like Earth is placed on it, it makes a dent. If you place something smaller like a ball near Earth, it will roll toward the dent. This is like how objects behave due to gravity, not a mysterious force, but a response to the bending of space-time. General relativity gives a solid explanation for how things move in our solar system, like how the planets orbit the sun. It can accurately tell us the paths these planets take, including how Earth follows an oval-shaped orbit around the sun. According to Brian, this is different from the old idea of gravity simply pulling things, which struggle to explain how planets move the way they do. The new idea is that space and time are curved like a flexible fabric, and that fits better with what we observe. A big moment that confirmed general relativity was correct occurred during a solar eclipse in 1919. Sir Arthur Eddington led a team to see how light from distant stars bent as it passed near the sun. According to the theory, the sun's massive mass would cause the starlight to bend a little. During the eclipse, the observations exactly matched Einstein's predictions, establishing the validity of the theory. Just like motion can change how we experience time according to special relativity, gravity also affects time. Where gravity is really strong, time moves more slowly compared to regions with weaker gravity. So, if you were standing near a massive object like a black hole, your clock would tick more slowly than one set far away from the strong mass. General relativity introduces black holes, which are places where gravity is extremely intense. Inside a black hole, the gravitational force is so strong that nothing, not even light, can escape from it. The boundary around a black hole is known as the event horizon, and it's like a point of no return. Once something crosses this boundary, it's pulled into the black hole with no chance of escaping. Einstein's general theory of relativity has huge implications for how the universe is structured. Initially, he added something called a cosmological constant to his equations because he thought the universe was static. But when we discovered that the universe is expanding, he called this a huge mistake. The idea of an expanding universe, based on general relativity, is a key part of the theory of the universe's origins, explaining how the universe began. Another important idea from general relativity is gravitational waves. These are like ripples in the fabric of spacetime caused by really massive objects moving fast, like when black holes or neutron stars collide. In 2015, scientists at the Laser Interferometer Gravitational Wave Observatory, LIGO, directly detected gravitational waves, proving another aspect of Einstein's theory. Over time, scientists have conducted numerous tests to check if general relativity is correct, and every time it has proven to be accurate. Whether it's seeing how planets move, the bending of starlight, or detecting gravitational waves, the theory has consistently been supported by evidence. While saying gravity is completely wrong may be surprising, especially since we all experience gravity every day. In the world of physics, it's common to discuss and investigate different ideas. Scientists like Brian often challenge established theories, and with gravity, some people question the conventional way we think about this fundamental force. One theory challenging conventional gravity is called modified Newtonian dynamics, MOND. MOND suggests that gravity behaves differently at low velocities, especially in universes without needing dark matter. Instead of adding invisible matter, MOND suggests that gravity becomes stronger at low velocities. The gravity debate also involves mysterious dark matter and dark energy, introduced to explain certain phenomena in space. Critics argue that these may not be necessary, and alternative ideas can explain what we observe. Some researchers who disagree with Einstein's gravity theory explore other possibilities, like theories involving unknown particles or forces that could alter or contribute to our understanding. It's important to understand that in science, groundbreaking ideas aren't overlooked. They are carefully tested to see if they make sense. For example, Einstein's idea of time in four-dimensional space, where time travel into the past may be limited by the speed of light, has been creatively explored alongside ideas like wormholes and shortcuts. Stephen Hawking's chronology protection conjecture proposes that time travel into the past seems unlikely from a physics perspective. Ongoing tests and observations check if these new theories can explain things like the strength of gravity in a similar way to what we already know. While alternative ideas have been discussed, none have convincingly replaced the well-established principles of gravity. Questioning and challenging ideas are vital parts of how science learns new things, leading to further investigation and a better understanding of the universe. In the world of gravitational theories, general relativity remains the most significant and successful one. Despite challenges and alternative ideas, it consistently performs well in tests and explains various phenomena like how planets move and how light bends around massive objects. General relativity stands strong because it's simple and covers a wide variety of phenomena. As we discussed earlier, Einstein's special theory of relativity suggests that time can behave differently depending on how you're moving. Now, let's explore how this idea affects real-world things, especially in space travel. Space travel is exciting but challenging because space is vast, and according to Einstein's theory, the speed of light is the fastest anything can go. This makes traveling between stars a huge challenge, even with cutting-edge technology, because of the long timescales involved in reaching the nearest stars. Consider the famous twin paradox to understand what happens with time when you travel in space. Imagine this: one twin stays on Earth, and the other twin travels to a distant star. When the space-traveling twin returns, they find that less time has passed for them than for their twin on Earth. This means they kind of travel into the future. Time is crucial for space travelers because the longer the journey, the more time slows down. If astronauts travel to nearby stars, where time slows down significantly, they might age more slowly than people on Earth. While it might sound like science fiction, it's a real effect from the theory of relativity. Imagine if humans sent a crew to a star system not too far away. Because it's such a vast distance, the journey might take many years, even if they travel fast. For the astronauts on the spacecraft, time would feel slower because of time dilation. Meanwhile, on Earth, much more time would have passed. Time dilation not only affects living things but also affects technology. Computers and communication systems on spacecraft need to account for time dilation to ensure accuracy and proper functioning. Space travel challenges at high velocities involve physical aspects, such as prolonged isolation and exposure to cosmic radiation, as well as the psychological effects of being away from Earth for an extended period. In our everyday lives, we can see the effects of time dilation in the Global Positioning System, GPS. GPS depends on the precise timing of signals from moving satellites. Since these satellites experience time dilation, it's crucial to account for these effects in GPS calculations. Failing to do so would significantly impact the accuracy of navigation systems. Now, let's explore why time moves in one direction. Time governs our lives, moving from the past to the present and into the future. This one-way flow of time is fundamental to our existence, but why does time have this one-way nature? To understand, we look at entropy, an idea that measures disorder or randomness in a system. Entropy is tied to the arrow of time, and it tends to increase over time, making time flow in one direction. The second law of thermodynamics expresses this relationship, stating that in any isolated system, total entropy will either increase or at best remain constant. In simple terms, entropy naturally tends to increase and doesn't decrease on its own. Understanding how things get more disordered around us helps us see the one-way progression of time. Imagine a deck of cards neatly organized. If we shuffle them, they become messy and random. This transition from order to disorder shows how time moves in one direction, as seen in everyday phenomena like ice melting or a stirred cup of coffee becoming messy. As the James Webb Space Telescope continues to explore deeper into the cosmos, it is not only advancing our understanding of distant galaxies, stars, and black holes, but also providing insight into some of the universe's most fundamental forces. For example, the JWST's ability to study the interaction between light and matter on a cosmic scale is opening new avenues for understanding how light behaves as it travels through space. This is crucial for better comprehending the universe's vast distances and the way information about distant objects reaches us over time. The telescope's capacity to capture the faintest signals from far-off sources means it is helping refine our measurements of cosmic distances, further enhancing our comprehension of the universe's expansion. Moreover, JWST's contributions to understanding the formation of supermassive black holes and their relationship to the galaxies they inhabit are advancing our theories of galaxy evolution. The new discoveries also point to the potential for future missions to study even earlier periods of cosmic history, offering a glimpse of what could lie beyond the scope of current research. This ongoing exploration is set to unravel even deeper mysteries about the origins of the universe and the forces shaping its future. As more data is collected, scientists hope to unlock the secrets of dark energy and refine our theories about the fate of the universe, offering answers to questions that have puzzled humanity for centuries.